All right, we've got Liran Liss talking about RDMA bonding.
This presentation is going to be about one of the fundamental problems that we have with smart offloading devices, such as HCAs. And that is, how do we have the ability to basically aggregate multiple links together for all the goodies that bonding provides us. And basically this covers the concept, and also I'll show some details about a prototype implementation that we've done. So I'll start with the introduction of what bonding is, then go over the concept of how we attack this problem, which is, we call it transport level bonding, and then a little bit about the design and the way we recover failures. So what bonding does is let you basically aggregate lots of physical links into one logical link. The motivation for this is both basically to enjoy the aggregate bandwidth of all these multiple links without basically managing each of these individual links on its own. For example, applications don't really need to worry about distributing their load between all these, across all these physical links, and still enjoy the aggregate bandwidth. The other advantage is high availability. So if one of the links go down, what you would want to happen is basically, as long as you have a single active link, you don't want the applications to even know about it. And the question is, can we do the same for HCAs? So let's look at a few concepts that are known in the industry for link aggregation. The first is the Ethernet standard. And I'm typically now concentrating on the host side of things, okay? So in the host, it's the typical solution for Ethernet bonding is to have a pseudo network interface called a bonding driver that sits between the physical devices and the TCP/IP stack. And this driver, basically, it receives packets and it delivers them in a stateless manner to one of the physical net devices. And all this process is completely transparent to the upper stack. And basically, the transport, like TCP or UDP in this case, they don't know even that any bonding is going on. And the packet just gets, multiplexed across the links, and if one link goes down, then they just steered to the remaining link, and everyone's happy. The problem with RDMA is that these net devices at the bottom are not stateless, right? They're stateful. They're actually running the complete transport. So there's no real way, if I have one HCA going down, kind of automatically migrating all its state to another piece of hardware. So this kind of approach doesn't really work for RDMA. The second type of bonding type is, I called it session level bonding. It's kind of what iSCSI does. So it has this notion of a session, and within an initiator target session, it can have multiple TCP connections. That's one option. Another option is to establish multiple sessions and kind of use the naming to present a single logical device using multipathing. And again, applications see a single disk, although you can access it from multiple paths. But what distinguishes this approach is that the whole concept of bonding these TCP sessions into TCP connections into a single section, it occurs kind of within the iSCSI HBA. It's not visible to the top of the stack. While in RDMA, what goes at the bottom, the transport to the bottom, is the same transport that application sees. So I can't hide the fact that I'm going to use multiple links or multiple QPs on multiple devices and make that transparent. And in addition to this, I have an HBA that's used by a single consumer, which is the SCSI subsystem. In RDMA, I have multiple consumers. So even if I solve this problem in a similar manner in a ULP, Like maybe SMCR does the same, but it's a single application. Maybe RDS can handle this in its own protocol. The thing is that if we push it to the upper layer, then we don't have a generic solution that everybody can enjoy from. Okay, so there are approaches that individual ULPs have done, but it's not a generic interface. So our goal was, how do we expose a standard RDMA device, and which any ULP can use, and still enjoy the benefits of bonding? So we came up with this concept, which we call transport level bonding. And what we do, sorry, is basically we introduce a completely virtualized HCA called the bonding HCA. And this HCA has a bunch of resources which are all virtual, and they're all exposed to the applications. So applications work with this device just like any other RDMA device. And it turns out this concept is not a new concept. The notion of virtual RDMA resources, it was presented in several pieces of work. First of all, in the IBM and Ohio State NOMAD paper, where they dealt with transparent RDMA migration. So they had this concept as well. Only what they did there, they implemented this notion of virtual resources at the hypervisor level. It was only used for virtualization. VMware VRDMA is also similar. So they don't really do pass-through. So they have a virtual HCA. And last year, Oracle presented the live migration prototype, which they implemented inside the MLX4 user space library, which also introduced the notion of virtual resources. This previous work, they used this concept of virtual resources to solve the transparent RDMA migration problem. And in all these cases, whenever the virtual machine was required to migrate, they had this very orderly way to close the connections, migrate the VM, and then reestablish the same connections. But when we're dealing with bonding, we don't enjoy this kind of negotiation. Somebody just pulls the link, and we need to recover from that. There's no time to negotiate. So the body of this work is, or the essence of this work is, how do we enable to recover from these abrupt link failures in a way that's transparent to the application? So the idea is basically to have link aggregation performed by this bonding driver. We distribute queue pairs, the physical queue pairs, between the different HCA links. By the way, we can bond both different physical devices and even devices from different types. We can bond together an InfiniBand HCA, a Rocky, iWarp. We can bond basically anything that satisfies the verb's operation primitives. So once we have a failover, we're going to basically reconnect on a different device and port, and we're going to continue traffic from exactly the point of failure. And what's neat about this thing is that we can treat transparent migration actually as a special case of high availability. So think of high availability as associating one or more links. If instead of that I associate 0 or more links, then the 0 links is live migration. So as long as I get the new link within 30 seconds, I don't tell anything to the applications, and I can support live migration with the same mechanism. Okay. So when we come to implement this idea, we pose several requirements. First of all, we wanted to support different physical HCAs. We wanted to have this idea implemented in a hardware-independent fashion. We wanted not to make any compromises regarding the semantics. We want to have the same ordering rules, the same visibility rules of I operations as verbs provides. We want this to be transparent to the applications, not only the way that we virtualize the resources, but also when a failure event occurs and we manage to recover, we want to do that in a transparent manner. And we want this solution to be extremely high performance, so people will actually use this without losing or hardly losing any performance compared to the bare metal case. So the design that we came up with looks like this. It's a completely user space design. The bonding driver is just a virtual provider like any other, right? It's I have here vendor 1, vendor 2, and the bond driver just plugs into the IB core just like any other vendor. And it means that the applications, if you do IBV dev info, you'd see IB0, IB1, or sorry, MLX for like 0, MLX for 1, and then bond 0. Just another device. And you can open, when you do IBV list device, you'll see this bond device. You can open QPs on it. There's no new API to access this device. In terms of the type of the device, we present it as a RoCE device with IP addressing. So the GIDS, the identity of the bonding driver, is a unique IP address. Since this is a user space solution, we want to coordinate across devices and across processes. The QP number is basically a port number from TCP port space or whatever. The HCA identity is an alias IP that we associate with the IP interfaces that we want to bond. Another design choice is to have a mapping which is a one-to-one mapping between virtual to physical QPs. And the reason for that is that we want to enjoy the hardware guarantees of ordering in the common case. So if you want to have high bandwidth, then you have to open multiple QPs on this device. But each QP is going to be associated with a single link at a time. This is actually not a new concept. Ethernet bonding does the same. It hashes on the flows, so a single TCP flow would always use the same link at every point in time. It's done to prevent reordering of packets. Another design consideration was to do the fast path in application contexts. So we have here quite a bit of new functionality to establish connections underneath the hood. But when everything is working, we want the actual fast path operations to occur without threads, without context switches, both when sending traffic and when pulling completion queues. Okay, so to show you a better picture of how this works, the top level box, the RDMA bond driver, in this example opened 2 QPs, which are associated with the same CQ and the same protection domain, PD1. And we have 2 memory regions, MR1 and MR2, which are again open on the same protection domain. And what the bonding driver does in this case, it maps VQP1 into some QP3 on HCA1, and then VQP2 to some QP9 on HCA2. And it still needs to poll completions and do stuff in a standard way. So what's happening here is we have the virtual CQ actually mapped to physical CQs on both devices. So whenever the user application will poll VCQ1, we'll actually poll CQ69 and CQ17 on both of the HCAs, since both of the QPs are currently mapped to the same virtual CQ.
How do you handle completion order?
On the same,
You have 2 different sources. How do you order the completions between them?
since each of my QPs is represented by a single physical QP, the ordering of that QP is guaranteed by the hardware. Between QPs, I have no guarantees in any case. If you associate 2 QPs with a CQ, there's no guarantees about the ordering in which they complete that CQ.
But the upper layer has no idea there's 2 CQs then.
Right. What change in semantics do you see here to the application?
You need to complete in the order they were posted.
Only with respect to the same QP.
Right, so your virtual Q pair 2 could get out of order completions back.
How is that possible?
If it went out on HCA1, if one
No,
work
it's
request went
not.
out on HCA1 and the other one went out on HCA2.
Okay, so let me
That's
clarify
what I was
something.
asking, right?
Virtual QP2 always is associated with QP9 and HCA2. It's never associated with a QP and HCA1.
Can you say that again? I'm sorry.
Yeah. Virtual QP2 is always associated with QP9 on HCA2. It means that any work request that's posted at virtual QP2 always gets completed in order on the hardware CQ17.
Sure. But
So
CQ1 pulls from CQ69 as well as 7.
yeah. Again, you need to look at the work requests that were posted to QP2. Are they ordered? And the answer is yes.
Okay. Well, then I have a second question. How do you schedule events that occur on those two CQs with respect to CQ1? Let's say an interrupt occurs. How does VCQ1 receive the completion notifications from two CQs at once?
We'll register for completion events on both of these CQs, and whenever one of them fires, I'll just call the application handler, and it'll poll, and it'll get poll from either CQs. It won't know that it's polling either CQs. So another interesting thing that I'd like to point here, well, first of all, we've needed to create two protection domains, right? One on each physical HCA. The reason is because we have to, right? We have no other choice. We have to create protection domains. And regarding the MRs, although we have two memory regions that are associated with the same protection domain, let's assume that until now, the first MR has only been used on virtual QP1, and the second MR has only been used on virtual QP2. So in this case, I'm not creating a physical resource for this MR on both of the HCAs. I'm creating it on demand only on the HCAs that actually is using it. I mean, this is just an example. Maybe you can cache it. Maybe you can garbage collect resources that are not used. This can be, complicated or optimized in any way. But at least for a certain traffic pattern, this is kind of exemplifies how the objects are organized.
How do you know the MR has been, quote, used on QP1 or QP2?
Whenever I encounter a work request that specifies that MR.
What if it wasn't in a work request? What if it was in the upper layer payload?
I need to establish the MR, the physical MR, only when it's actually used. I mean, if you just transfer the key, I don't care. Another thing that we need to do, we do need to translate remote keys. So each of these virtual QPs, let's assume that these are reliable connected QPs, they also have to hold a translation between the virtual remote keys and their physical keys that their peer HCA is using. So whenever a remote key is encountered the first time, we'll query using an out-of-band protocol the resolution of that virtual key to the actual physical key, and that's what we'll use for further work request operations. So,
what happens for the incoming read and write?
pardon?
What happens for incoming read and write?
So in that case, my remote peer would query my local node for a resolution between its own virtual R key that the application has provided, and translate that into a physical R key. And from that point onwards, it'll just do straight read and write from hardware.
Excuse me? The peer will query the key mapping prior to issuing the RDMA read?
Yeah, in a transparent manner.
And then it will cache that mapping?
Yeah.
Okay.
Yeah.
I don't think I can use this driver, ever.
Why not?
Well, because I'm probably going to destroy that mapping after every operation that uses it. And so you're going to be querying it constantly. I'm also probably not going to trust that I've got two drivers chatting with one another, transferring some rather sensitive information from host to host. I'm still not sure how you handle retransmit. You say you reconnect and reissue the request when you drop one of these things. You'll get there, I'm sure.
Yeah, I'll show you that
All
in a
these
minute.
things worry me a hell of a lot.
Well, first of all, regarding invalidations, then if someone has shown interest in my remote key and I invalidate it, I can let him know that the key is invalidated. But in any case, this is a one-to-one mapping between a virtual resource and a physical resource. If I invalidate any, and the remote peer, let's say, maliciously tries to use the old mapping, the actual physical key and hardware is invalidated. It's going to get a protection violation error.
Right,
You're-
as you usually would.
Yeah, as it usually would, exactly.
It could be reallocated by that time.
But I have another way to learn
Yeah.
that key. I can send you an evil query that maps to that key and learn what it is and issue an RDMA operation, right?
What, the new key?
Yeah, whatever the currently valid key is. I have another way of finding it. I have the upper layer that sent it to me, but I can go in, sneak in the side way and ask another way what that key is, right?
Well, I'm not going to tell you anything about the key unless it was previously registered. So,
But I won't lose the connection when I query you for the key, so I can just
Yep.
keep trying.
yeah, you can.
It's a terrible security problem. Okay.
How do you leverage the data continuity after the failure?
Sorry?
How do you leverage data continuity
Yeah.
after link failures?
We'll get to that in a moment. We'll get to that in a moment. So this is kind of the basic idea. Again, think about the data path. We want to do everything in the application context. So when we pull CQs, actually we use the application pull CQ context to actually pull the list of associated hardware CQs and extract completions from them. Let's look at these basic operations and how they're done. So when we're posting work requests, basically we have two phases. The first is to insert the work request into the virtual QP. So if it's not suitable or the virtual queue is full, I return an immediate error. And then the first milestone is to enqueue the work request into the virtual queue. Now, there could be a mismatch in size between the virtual queue and the physical queue. So maybe the physical queue is full, and then I just return success, and whenever there's completions, I'll keep on working. If it's not full, I can continue. If I'm doing a send, I check if the connection is active. If it's not active, I can schedule a reconnection, just go out, so I won't have the application waiting until I reconnect. If the connection is okay, we can continue. For UD, we need to resolve the address handle. I'm going to skip it right now, not going to this details. For RDMA, we need to resolve the remote key if it's not already cached and resolved. If I'm doing a receive and the connection is not currently active, I just return success. I'll post the receives whenever the connection is established. So the connection is established on the first wikis that's posted to send, or whenever I have a failover event. If everything is fine, I'll translate the scatter-gather entry to the actual hardware names and post it to hardware. So this is the post-send flow. Polling completions is also interesting. Basically, we want to poll the next hardware completion queue that's associated with the virtual completion queue. And if the poll succeeded and the hardware completion queue is not empty, I have this couple of interesting cases. So the first is if I have a retry exceeded error, and what I'm going to do now is instead of reporting to the application a retry exceeded, I'm just going to schedule a reconnection and just ignore this completion, as if the completion queue is empty. If I have a flush error, I'm also currently going to ignore this completion, because whenever I have an error, I report the error and put the QP, the virtual QP in error state. We'll see in a moment how we generate flushed and error completions. If there is success, I'll return the successful completion. Any other error, it means that it's an actual semantic error, right? It's not due to losing the connection. So I'll modify the virtual QP to error state, report the error as completion, and I'm going to add the virtual queue, the virtual send queue or receive queue, whatever I was polling, to a per CQ error list. And this error list is what allows me later to report flushed in error completions. If I've completed this hardware polling, I go to the error list, see if I have some virtual queue in the error list. If it has in-flight Wookiees, the producer is not equal to the consumer, I'll generate a flushed in error for the next Wookiee. And I keep doing this according to the number of completion entries that the user is required as asked for. And if one of these cases returns true. If I polled all my work queues on the error list and all my hardware CQs, I'll report that the CQ is empty. So in the common case, if you have if you're using a dual ported HCA, I might even open a single hardware CQ, so I'm not even polling two locations. If you're using two devices, I don't expect people to, to link aggregate lots of devices, probably two HCAs or two ports on each HCA. So in the worst case, I'm only polling two physical CQs for one poll CQ operation that was asked. So there was a question asked about how do we recover for failure. So it works like this. The first thing we do after failure is that we reestablish a connection. And we can do that over any active link and any device. Doesn't have to be the same hardware or even the same hardware type. After we do that, let's look at the example here. I have a connection, and let's say I have here in this example, I have a send queue and a receive queue. I have the virtual producer is basically the last Wookiee that was put on the virtual queue list. The physical producer is the last Wookiee that was posted to hardware, and the virtual consumer is work queues that have been completed. So let's say that I lose my connection and I don't have any hardware anymore, so I'm left only with the virtual producer and consumers on both ends. So in order to recover, I reestablish the connection. Then what I do, I negotiate the last committed operations with my receiver during this reconnection process. And as it was, look at the point here before the link failed. The dotted arrow basically signifies a point that should have been the consumer if acknowledgements were received. But let's say that I posted a bunch of work, my receiver virtual consumer has advanced, but the acknowledgements have not yet been received on the send side when the link went down. So when I reconnect, I kind of get this information and I advance my virtual consumer to the point of that dotted arrow like this. This is how I ensure that I don't retransmit old work. And after I do this, I rewind my physical queues by establishing, basically sending work on my new piece of hardware from the location, the exact location of the virtual queue that was not yet transmitted.
How do you name the request so you can detect the replay? I mean, it might be a new type of device with a new QP number and all that.
So the identity is an IP address and a port number from the TCP port space in RDMA ACM. So it's globally unique in the system.
Endpoint, but what names the request? The actual send operation.
Internally, I mean, the bonding drive internally uses RDMA ACM for all of its connections. So, and it itself has an identity of an IP address. So whenever you're reconnecting to that same IP address, and the QP that you want to connect to is a listener RDMA ID that basically the port number of that listener RDMA ID identifies the QP. So you know exactly which device and which QP you're connecting to.
How do you detect recycling of port numbers? Could be a totally new entity.
Time weight. We haven't gotten to that stage in the prototype, but basically time weight.
So a number of file systems have this concept. It's
Right.
called a replay cache, and it's one of the most difficult things to get right. It's also very resource intensive.
Yeah.
Very like
So all this reconnection and negotiation and knowing where to resume transmission is a complex operation. But after we complete that, when you're back on track, then
Oh,
it's
yeah.
really minimal overhead to
Oh
continue.
yeah, everything's
yeah.
great once everything works.
Yeah.
Right.
Yeah.
The QP number seen by the application is just the port number in the TCP port space.
Yeah.
So does that
Uh,
reduce the
Let me go back here a moment. Probably I should have mentioned it. Wait a second. Okay. So each virtual QP has two RDMA IDs. One is the listener RDMA ID, which is the QP number. Okay, the port space is basically it's only 16 bits, but so we have only 64K QPs on this device. But it uniquely identifies this virtual QP on this machine, regardless of the physical hardware that we're going to use. And the connection RDMA ID is the current connection that I'm now using for this QP, if it's connected.
Do you round robin or balance the
reducing
QPs?
the total number, the fact that we are reducing the total number of QPs to 64K, as seen by the application, even though we are trying to aggregate resources from two different HCAs, kind of beats the purpose.
I'm sorry, I didn't hear the question.
I'm saying the fact that we are reducing the total number of QPs, as seen by the application, to be 64K, but we are trying to aggregate resources across two HCAs, kind of beats the purpose, doesn't it?
I don't know. I'm not sure that there are so many, let's say, standard applications that opens thousands and thousands of QPs. Probably there are, but I mean, again, this is a prototype as a user space only solution. Maybe if we would have something that also has a kernel component, then we can solve. We need to solve the problem of having unique resources across physical HCAs and across processes that don't speak with one another. If we would extend this implementation of the kernel, we could probably alleviate this limitation.
Are you able to detect, for example, when you have two machines and they have two switches between them, and there is a failure of the link between the switches, so not the immediate link that you are connected. Are you able to detect that situation and to make that some representation or just renegotiate that session? So just
Not in this prototype. We're just going to try a different port and see if we can reconnect. If we can't reconnect, eventually we'll report retry exceeded and flush an error.
So if an existing user application, let's say, is already using RDMA CM and is dependent on, let's say, address change events to come to know that, the address is payload of the other port or other device, etc. So if this bonding driver sits underneath such an application, you're saying it won't get address change events?
At this stage, we implemented integration only as a verbs device. We didn't integrate yet into RDMA CM, so I can't tell you any details about that yet. So the current status of this prototype is that we supported basic objects, protection domain CQs, RCQPs only in memory regions. We currently only did send-receive tests, and we support all of the manipulation of these virtual resources, and we currently handle the failure of a single link. So if we pull out the plug and then we kind of reconnect it, and then it reestablishes the connections and attempts to continue the work. Actually, even this kind of functionality can basically support transparent migration, because this is basically what it does. You have no link for some time, and then you have a link afterwards. Next steps are to complete the coverage, to think about integrating the RDMA CM, and add this multi-link recovery. So we probably need to, whenever we have the initial connection, we try to maintain the latest information of which are the active links of our remote peer. So if something goes bad, we know which links to try. And once we have multiple links, we can do all kinds of fancy aggregation schemes. high availability, just load balancing QPs in round robin fashion, but also neat stuff like dynamic load balancing of RC QPs. So we can have an RC QP if we have like most of the traffic currently hitting this first device, that we can transparently move this RC connection or a bunch of them to another device, and all this in a transparent manner to the application. Okay, so in summary, we've found a bonding solution for stateful devices. It's hardware agnostic, so it's just a standard driver that plugs into OFID. You don't need to, it's not tied to any hardware. You can tie ports for different devices. The only limitation here is your peers have to be bonding drivers, right? Because we have this out-of-band protocol. When we reestablish connections, we need to negotiate the state. You can't connect to a native Rocky device. You need to connect to someone that supports the same abstraction. So if you want this high availability, you just need to install the bonding driver in your cluster and just open connections from bonding driver to bonding driver, and you can enjoy this functionality. It potentially supports, high availability, aggregate bandwidth, load balancing, and transparent migration. And we have a very efficient user space implementation. Bandwidth is more or less the same. Latencies, we've seen degradation between 5 to 10%, but other than that, we achieve the same hardware latencies. And we think that the same scheme could be extended to the kernel. Yeah, please.
Would it work with just a single HCA port?
Yeah. So the use case for a single HCA port is transparent migration. Any more questions? Okay, thank you.